Hi there, this is Tony Verbsky. Actually, you can call me Verb, V-E-R-B. Been at Metro State for 25, 26 years. Taught trig probably 75, 80 times. Um, I think we're going to do okay here. This is my first online class. I'm going to try to give you lecture notes, kind of like a traditional class. I highly encourage you to do your reading. And then I'm going to help you through your MyMathLab, also called MML. Today's lecture is basically about angles. If you need to contact me, give me a text at the number you see right there, 720-985-1986, or give me an email. I'm only going to lecture over the things I think you need help on. The book is fantastic. The reading in section 9.1, which, by the way, you'll find the textbook in MyMathLab under contents or HTML version of the book. Well, anyway, let's get started here. So basically, angles in math class are measured off the positive x-axis, called the initial side, labeled in red, and then you turn and burn counterclockwise, and this is called the terminal side. Now, there's two ways to measure angles. There's decimal, and there's old school degrees, minutes, seconds. This textbook loves some of the old school stuff. It doesn't go away, so we got to learn how to use it. Everybody in the world prefers decimal, but back in the day, that's what they were restricted to. It's like clock arithmetic. So let's talk about this. This angle to me in my picture, I'm just guessing, is about 58 degrees, 14 minutes, 36 seconds. Now, if you think of degrees as hours, 58 hours, 14 minutes, 36 seconds, you're probably going to be better off here. What I'd like to do is convert this to decimal. So we have 58 degrees, 14 minutes, 36 seconds. All this really is 58 degrees plus 14 minutes out of 60 minutes in 1 hour, plus 36 seconds over 3,600 seconds in 1 hour, and we get 58 point, well, let's get out the TI 8384. Hopefully this thing works and doesn't crash my computer. 58 plus 14 divided by 60 plus 36 divided by 3,600. And we get 58.243 repeating degrees. As I said, we prefer decimal. Old school transits used to have. That's something you look at to maybe determine the height of something the surveyor would use. They'd have a degree dial, they'd have a minute dial, and they'd have a second dial, and they tune it in the best they could, and they just take their reading off the side. These days, the transits and all these surveying equipment are actually decimal and fully digital. So anyway, our book has a, I don't want to call it unhealthy, but a traditional approach, and they would like you to understand degrees, minutes, seconds. Now, I'm not even going to try to hide anything from you here. This calculator, TI-84, 83, this family is really awesome. So you can actually go 58 second angle degrees, 14 second angle seconds, and 36 second angle. There's no double tick. Some programmer at TI probably got fired over this. they actually put that double tick down here on this plus symbol. So you got to get out, second quit. Then what you got to do is you got to get back in, go down here, so not second, alpha, enter, get the double tick, hit enter, and it rolls it over into what we had. I personally find it easier to just type in what I had above instead of cheating and using that feature. But hey, I'm going to show you where everything is. Hey, I got a calculator right here. You know, calculator usage is important. Well, anyway, what we need to do is also learn how to go the other way. So let me see what I can do here. I'm gonna maybe create a new page. What happens if somebody gives you 36 degrees? Oops, excuse me. How about 36.147 degrees? I just had to move the degree symbol. Well, obviously, it's 36 degrees, blank minutes, blank seconds. So what we do is we subtract 36 and we pick up a 0.147. 0.147 of an hour, really of a degree. So what you do is multiply by 60. 60 minutes in an hour, 0.147 times 60. And we get 8.82 minutes. So we move the 8 right up into there. Let me move some of my stuff around. There we go. Move the 8 right into there. Where's my red? Right into there. And what you do is you subtract 8 and you got 0.82 of a minute. Well, you multiply by 60 because there's 60 seconds in a minute, and you get, so on my calculator I subtract 8 and I go times 60 and I pick up 49.2 seconds. Now, if this number is 5 or over, you call it 50. Since it's 5 is less than 5, we go with 49. So I do like the calculator actually better for this. So if I go 36.147, 36.147, there's that angle feature, second angle, convert to degrees, minutes, seconds. Oops. Oh, here. 36 point, what was it again? 147. Second angle, convert to DMS. And you can see I get exactly the same thing, only when you're working MML, you're going to have to put 49. Don't put 49.2. MML will care. So that's the start. Now, what you need to do is be able to add and subtract. For example, 23 degrees, 14 minutes, plus 47 degrees, 58 minutes. Well, I prefer to stack it up, so I'm going to go old school here. It's kind of like clock arithmetic. I don't know how old you guys are. I'm 52. Bottom line, I went through this when I was young, fourth grade. 12, 1, 75, 0, 70 degrees, 72 minutes. But you know there's 60 minutes in a degree, or 60 minutes in an hour, so it's 71 degrees, 12 minutes. So that's basically how you do addition. Obviously, if this 58 were smaller, the problem would have been a lot easier. Next topic is coterminal angles and standard position, and basically the Cartesian coordinate system broken up into 4 quadrants. So in Cartesian coordinates, all we really mean is the XY axis. And this is known as quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Also known as the plus plus, the minus plus, the minus minus, and the plus minus quadrants. Looking at X, Y. As mentioned, we measure angles. Missed that one. Here we go. Make it bigger. We can have an initial side, which is the red, and we can have a terminal side, which is the blue. Let's pretend that this angle is 120 degrees. Now, an angle is said to be coterminal if it shares the terminal side. So I'm going to use 3 equal signs to mean almost equal, because they're really not equal. They're just coterminal. So if you measure clockwise, which is in reverse, this is a negative 240 degrees. So it's equivalent to negative 240, but really I mean coterminal. But there's more. You can actually go 120 and 360 more. 480 degrees. Keep adding 360. Let me see if I can do this. 840. And you also can keep subtracting 360, and you can get a whole bunch of terminal angles. Angles with terminal sides, said to be coterminal. Now, we use more than degrees. This class starts off pretty fast. A lot of books wait to do this, but not yours. And actually, I prefer this. We're going to introduce radians today. First day. It's a different way to measure angles. So, next topic, radians. What we're simply going to do is look at a circle of radius r. So this point is r0, and there's the radius r. I like to bring back the circumference formula of a circle, which is pi r squared. Correction, 2 pi r. When I'm lecturing, I'm actually thinking about 30 seconds ahead of where I'm actually at, so occasionally that happens. Anyway, in this situation, the associated angle would be theta equals 360 degrees if I would like to go all the way around the circle. Now, what we're going to do is we're going to try to place this point exactly where it is again, but another way to say this is basically get your compass out, draw a circle of radius r, and then measure with a flexible tape measure 2 pi. And 2 pi is about 6.28, and it puts you right in the same spot. So we're going to say 360 is equivalent to 2 pi radians. Now this is a little different. Degrees, you get your protractor out and you can see, 360 degrees, 35 degrees, but radians is actually a distance measure. So it's really 2 pi, could be feet, whatever units are, but we say, when we're saying it's equivalent to an angle, so 360 degrees gets us to that point, but if you take a compass and make a circle of a radius r and measure along the arc, you get back in the same spot. So basically, we made a new relationship. It's way different than inches and centimeters, but still, it's equivalent thing. Basically puts you back to where you were. Now, based on this, 360 being equivalent to 2 pi. Now, nobody actually writes radians, but sometimes in this class we're going to write it and sometimes we're not. So 2 pi radians, which means 180 degrees is equivalent to pi radians. Now, when you say 1 inch is 2.5 centimeters, and you want to convert back and forth, you create a ratio. And these ratios are equivalent. So you can use 180 degrees over pi is basically a funny looking 1. And pi over 180 degrees, they're not really equal, but their ratios and their value, since they're the same thing, their value is basically 1. You're not changing the problem when you multiply or when you're converting units. Okay, so let's start with 90 degrees. 90 degrees, based on this, is clearly pi over 2. But if you look, sometimes I lack common sense, but if you need something that just works all the time, you would just go 90 degrees. I'd like to get rid of degrees, so put the 180 degrees on the bottom, and that's pi. So 90 over 180 is 1/2. I get pi over 2. This is the fast way. This way works every time. So let's do it again. 30 degrees. Let's do it the slow way. 180 degrees. Pi. 30. 130, 6 30s. Pi over 6 radians. The fast way. Pi is equivalent to 180. And I know I just basically divide by 6 both sides, and I get pi over 6 equals 30 degrees. But if I ask you 40 degrees, it's not going to work very good, the fast way. But if you multiply by basically a funny looking 1, zeros cancel, you get 4, 2, 9, straight across, 2 pi over 9. Now, you may not understand radians, but we can say 8 pi over 9. I want to get rid of radians, so you put radians in the bottom, you put degrees in the top, and this is really cool. The pi's cancel. 180 is 29s, and I get 160 degrees. Pi over 15 times 180 over pi. And then whatever 180 divided by 15 is. Oh, this is hurting. Should know this. 12. Yes. I'm going to double check. 12 times 5. 15. 10, 1, 5, 6. Woo, okay. Check. All right, so that's how you convert back and forth from degrees to radians. It takes a while to get comfortable with radians, so just know, it's not something, put it this way, it's best to introduce it now instead of waiting, because you'll have more time to absorb how you're gonna, when somebody says 5 pi over 6, and then down the road, that's 150, but right now it's just 5 pi over 6. It's like the square root of 19. I don't know. I don't really care what it is. Kind of right now, that's where you are in radians. 7 pi over 8. Have no idea, don't care. But you could convert it if you had to. All right, this section's a doozy. We got another concept. It's called arc length. Now, arc length is kind of 8th grade mentality. Let's say, well, it's a whole circle. So that's really bad circle. But what we're going to do is we're going to look at this blue arc. Now, it looks like about 50 degrees to me. And I'll say that it's 10 centimeters. And what I'd like to know is this distance here, S, which in math they call arc length. Now, basically, you know the circumference of a circle, 2 pi r. Now, what you're going to do is just multiply by 50 degrees over 360. So, in this case, it's in the 10, 20 pi times 50 over 360. And man, I'm gonna go for it. 20 and 360, 18. 50 and 18, 25 ninths. So 25 pi over 9 centimeters. Now, I don't know what that is. I want to know, though. Come on. 25 pi divided by 9 equals 8.726 centimeters. Now, so we got this formula, arc length equals 2 pi r theta degrees divided by 360. I'm going to multiply it by 180 over pi. I claim I'm converting to radians. So we cancel 2, cancel, S equals r theta. Radians only. This is a great formula. It cleans things up. Just know in calculus we never use degrees, we always use radians. Radians is like basically a natural measure where it turns out that the degrees were kind of a made up thing. So in calculus, the radians is definitely going to work out better. That was a very simple explanation. Simplistic, I should say. It's a little more complicated than that. Let's just leave it at that. Well, anyway, so we got this great formula now. So if you actually know the radius is 12 feet, and you know theta is pi over 3 rad, then you know S is 4 pi, because it's just 12 times pi over 3, which of course I want to know. We should almost know that. 4 times pi, 12.56. I'm going to go 5, 6, 6. You see how the third digit, the fourth digit is 3. So in class or during lecture notes, I'll either round it off or truncate it off. This time it's the same. Truncators don't look at the 3. Rounders look at the 3 to make sure it's not 5 and above. Then anyway, I'll go 12.566 feet is the arc. Now, we got another formula. One more. Same deal. We got an arc. And let's say theta, let's try to pick a nice angle, 40 degrees. Actually, it looks more than that. It doesn't really matter. And this is 10 inches. Now I'd like to find the area of the sector. So the area of the sector, of course, is pi r squared times theta in degrees over 360. So I can find it 100 pi times 40 over 360 100 pi over 9 inches squared, which is, can't help myself, 100 times pi divided by 9, 34.906. I truncated this time, inches squared. If I'd have rounded, it would have been 0.907. By the way, MML, they're always rounding no matter what. So, same thing as last time. What I'm going to do is I'm going to actually multiply by 180 over pi. So we got this formula, area of a sector, and we said it was pi r squared theta degrees over 360. But I'm going to multiply by 180 over pi, 180, 362, and I end up with 1/2 r squared theta as my sector area formula. Rad only. Now, I must tell you that this book has its pet problem. So the pet problem is basically like a sprocket problem, pulley problem, but I'm going to just quickly go over it. Bottom line, if these wheels are turning towards each other, and let's say it's like a stick of gum, you're going to shoot through there, and it comes out right here. Let's actually make the part that came out red. So the little wheel turned about that much, but the big wheel turned less. So this, the angle the big wheel moved is definitely a lot smaller than the little wheel turn. Now the little wheel is clearly turning faster than the big wheel, but the distance they travel is the same. So arc length little equals arc length big. Arc length little equals arc length big. But that's r little theta little equals r big theta big. Now what the book is going to do to you, they're going to give you 3 to the 4 and you solve for the fourth one, but you know it's radians only. But that's when you use the equation by itself. If it's since it's equation, whatever you multiply by, you can turn around and divide by it because you're just trying to solve an equation. So in this situation only, radians or degrees works. But outside of this example, I can't think of another one. Just stick with radians, play it safe. But on this problem, it seems like MML always gives you degrees. That was quick and dirty. There's still more. There's still more. This is a big section. Now, here we are. And we got this point. Some point x, y. And what we're going to do, kind of like a ball on a rope, and you got to kind of think that it's in motion. You're swinging it around and around and around and around. Now, pretend we're riding a car, that the car is tied to a string, and you're going around and around and around. You can look at your speedometer, and you can find your velocity, your regular velocity, like miles per hour. Now, since we're on a circle, the angle is also changing, so the angle has a speed. So we're going to define omega, really looks like a W, right? To be theta over time, degrees per second, radians per second, as angular velocity. Makes good sense. So what I want now is I want two speedometers in my car. I want an angular velocity meter and just a regular old velocity meter. By the way, regular velocity is linear velocity in this context. So if you ride around in a circle, you could have two speedometers, a regular velocity and an angular velocity. But wait, when you're a little kid, distance equals rate times time. But now you're in college and everything, college level classes, so you don't get to use rate anymore, you got to use V for velocity. But in this situation, the distance we're talking about is actually arc length, but only in a circular situation. So D is S equals VT. But S, we just learned, was R theta VT. Because that's the new formula, remember, rad only, radians only. Now just for fun, divide both sides by T. Now, theta over T, sorry about writing so big, theta over T is omega. So this theta over T is omega. So what I managed to do is relate regular velocity to angular velocity. Now, there's certain standard problems that go with this also, that you're going to need these formulas. So don't forget about this part of the lecture, or don't forget about reading your textbook. But when a bike tire, whoa, sorry about that. I'm going to go to the next page. Sometimes I lose a little track. So here's the bike tire, 13 inches radius. But I give you something like it's going at 200 revolutions per minute. Basically, I'm almost giving you the angular velocity. What I'm going to do is get rid of revolutions, but I want radians. In one revolution, that's 360 degrees, there's 2 pi radians. So the revolutions cancel, and I actually have 400 pi radians per minute. And that's omega, or W. That's angular velocity, degrees per minute, radians per minute. So I got this new formula. It is V equals R omega. So V equals 13 times 400 pi. Now, if you're paying close attention to the units, it's inches, radian per minute. It's said to be dimensionless. Nobody actually writes the words radians. We just said the degrees were equivalent to the distance around. If you want to have some fun, go to some math blogs and look up what it means to be dimensionless. You might be there a while. 13 times 4 is 52, so 5,200 pi inches per minute. And that's your linear velocity. Unfortunately, I don't understand that. So let's go back to our childhood days and convert to miles per hour. In 12 inches, there's 1 foot. And we live in Denver. Mile, 1 mile, 280. Let's get rid of minutes and bring in hours. And 1 hour, there's 60 minutes. Let's get out our handy calculator that I somehow closed, and I'm scared to do this, but I will do it in front of you anyway. Whoa, hopefully my pen doesn't lock up. There we go. Got some driver issues. So 5200 pi divided by 12, enter, divided by 5200, enter, times 60, enter. Oh, 15.708 miles per hour. All right, as said, I only do the things that I think you need help with. There's more I can say, there's a lot more I can do. Highly recommend you always do your reading. This book is awesome, especially the digital book through MML. If you go to log into the class and go course contents, go to section chapter 9.1. Beautiful thing is there's nice animations, there's interactive examples, there's things other than what I was doing. Then you go to your homework, click on section 9.1 and do the problems. By the way, you can work problems anytime you want till you get 100. You'll learn the game of MML. Anyway, that's it for today. Section 9.1 lecture is over.